Hi everybody! So in this video we're going to look at some fun experiments you can do with the quartz slice from Snellius Minerals. So the quartz slice consists of a piece of quartz that I've cut windows in so that we can actually view looking along the c-crystallographic axis and identify some pretty awesome features. In order to follow along with these experiments, you're going to need a polariscope. So if you have a polariscope, you're good to go. If not, you can actually buy some linear polarizers from Snellius Minerals as well and build your own at home. And if you want instruction on how to do that, you should check out the video Snellius Minerals DIY Polariscope. You can find these items for sale at the eBay store Snellius Minerals. The quartz slices come in a wide variety of types, and these are all cut from natural crystals. The differences in color that we see between our quartz slices are because of different impurities in the quartz crystal structure along with environmental conditions during their formation. So clear quartz is known as rock crystal. The gray to brown quartz next in line is known as smoky quartz. Purple quartz is known as amethyst, and yellow quartz is known as citrine. Let's take a look at some background information on the mineral quartz, which will prepare us to do some fun experiments with our quartz slices. I just want to start out again with the really big picture of what's going on here. We have a particular mineral, and that mineral is defined by its chemistry and structure. The chemistry and structure of a mineral also determine the crystallography we'll see at the macro scale, as well as the physical properties of our mineral and how those physical properties vary with direction through a crystal. In particular, we're going to focus on the optical properties of our minerals. So if all that sounded a bit like nonsense, what I'd suggest is taking a look at the optical mineralogy big picture summary video. There we do a deep dive for all these concepts on the mineral corundum. Let's now talk about some of these concepts specifically for the mineral quartz. The chemical formula for quartz is SiO2, and the structure of quartz consists of helical chains of silica tetrahedra. Now, I'd suggest in order to better understand the structure of quartz, you should check out some of the structure models on a website like Mindat. They have some really nice structure models there along with more information on this if you so desire. But the important part of this for us moving forward is that the chemistry and structure of our quartz are going to lead to the point group symmetry that we see in our macroscopic quartz crystals. In this case, the point group of quartz is 3,2. At the micro scale, the chemistry and structure of our quartz give us our space group symmetries, in this case P3221 or P3121. And the reason we have two of these is because it depends upon the direction those helical chains of silica tetrahedra actually spiral. We have two different options for them, and this is actually going to create some fun for us later with our optics. So the chemistry and structure of our quartz also yields the optical properties that we'll be able to view. Quartz is uniaxial positive, meaning refractive index epsilon is greater than refractive index omega. Some other important facts about quartz include that it has a hardness of 7. There's no cleavage, so no preferential direction of bond weakness in the quartz structure. The density of quartz is around 2.65 grams per cubic centimeter. Because the quartz structure doesn't actually have a center of symmetry, this allows quartz to be both piezo and pyroelectric, two important properties that actually make quartz one of the most important industrial minerals. And as we saw before, quartz comes in a wide variety of colors depending upon impurities and environmental conditions the quartz was subjected to. That's enough background information. Let's take a look at a macroscopic quartz crystal and try and understand the symmetry elements present. We'll start out here just rotating the crystal around a bit so you can get an idea of its shape. And this quartz crystal is also only terminated on one end. The other end was growing on something before it was broken off, and so one side of this crystal is terminated by nice crystal forms, and the other side is just a fracture surface. So hopefully you have a good idea of what the shape of this crystal is. Let's take a look in this particular direction because this direction is going to be important to us in understanding our quartz symmetry. The point group of our quartz is 3, 2. And what this means is that our quartz is going to have a single threefold rotation axis as its c-crystallographic axis, and then in a plane perpendicular to our c-crystallographic axis, we're going to have three twofold rotational axes as our a-crystallographic axes. The quartz crystal we're viewing here isn't exactly perfect, but given the hexagonal shape we're seeing down this particular axis, we can figure out that this is actually our threefold rotational axis for our quartz crystal. Therefore, we are looking down the c-crystallographic axis of our quartz crystal. Furthermore, we know our a-axes are going to be twofold rotational axes lying in a plane perpendicular to our c-crystallographic axis, and so we can add them onto our image as such. For today, this is a bit of a simplification of what's going on with the quartz symmetry, and we really could do a deeper dive into why what we're seeing here is actually a threefold rotational axis and not a sixfold rotational axis for our c-crystallographic axis. Without getting into too much detail, the form that is terminating our crystal may appear to be a hexagonal pyramid, but it's not. It's actually two distinct rhombohedrons. We'll save unpacking that for a different video. Let's now take a look at our quartz crystal along the plane of the a-axes. In particular, let's orient our crystal so that we can actually look down one of the a-axes. And I actually made all my figures using the next a-axis, so we're just going to rotate a bit further here. So we've now oriented our crystal so that we're looking down one of the a-crystallographic axes. So let's label this axis. So this axis should be a twofold rotational symmetry element. However, because our quartz crystal isn't terminated on both ends, you can't really see it in operation. So let's add on our other a-crystallographic axes in this plane, and then we can also add on our c-crystallographic axis and how that relates to the plane of the a-axes. We've oriented our quartz crystal crystallographically by using symmetry elements. And we've got two particularly important views of our crystal, one looking down the c-crystallographic axis, and another looking down the plane of the a-axes. So these two different crystallographic directions through our quartz crystal are important because our quartz is actually anisotropic with respect to a variety of physical properties. What that basically means is the quartz is actually going to behave differently in different directions through the crystal structure. And we'll be able to see this anisotropic behavior when we take a look at our optical properties. Going back out to the big picture, we've effectively explored the macroscopic crystallography of a quartz crystal and showed how the point group of quartz, 3, 2, relates to the crystallographic symmetry elements present in our quartz crystal. Let's now explore the optical properties of our quartz crystal. And in order to do that, we're going to have to look at the optical indicatrix for quartz. The optical indicatrix is a three-dimensional representation of the refractive indices of a substance. So here's an example for quartz, although the differences between the axes are exaggerated for demonstration purposes. If you want some more information on optical indicatrices and where this came from, you should check out the video Optical Mineralogy Anisotropic Materials, or possibly Optical Mineralogy Uniaxial Materials. So in taking a look at the optical indicatrix for quartz, these are two different views of our optical indicatrix that are going to be particularly important to us. And what I want you to notice is that our different refractive indices, here represented by omega and epsilon, align rather nicely with our crystallographic axes. Refractive index omega is aligned with the plane of our a-crystallographic axes, and refractive index epsilon is aligned with our c-crystallographic axis. Now that we've taken a look at the optical indicatrix for quartz, let's go and investigate the optical properties of our different quartz slices using a polariscope. So let's take a look at a slice of clear quartz, also known as rock crystal, with our polariscope using transmitted plane polarized light. So given our previous investigation of the crystallography of quartz, When you see this shape, you should think, hey, we're looking down the c-crystallographic axis. And that also means we're looking at this view of our optical indicatrix for quartz. And in this view, we're only going to see light that interacts with refractive index omega. I should also mention with my current polariscope setup, our plane polarized light is vibrating in a north-south direction. So with our polariscope in this configuration, the phenomena we'd be looking for in plane polarized light is pleochroism. So that's a change in color of our sample as we rotate it. However, given the orientation of our quartz, looking down the c-crystallographic axis, we shouldn't see any pleochroism as we rotate the sample, because our plane polarized light in this direction through our crystal is only interacting with refractive index omega. So our view along the c-crystallographic axis in plane polarized light is pretty boring. Let's switch our view now to looking along the plane of the A-axes. And I'm just going to quickly rotate the quartz crystal here because I want it to line up appropriately with all our diagrams. So now we're looking along the plane of the A-axes of our quartz slice. So hopefully this makes sense how this is oriented in space. Now let's bring in our optical indicatrix so that we can talk a bit about the optical properties we expect here. And when viewing our quartz along the plane of the A-axes, we should be able to transition between views where our plane polarized light is aligned with refractive index epsilon and views where it's aligned with refractive index omega. In this case, that means that we can possibly observe pleochroism with this orientation of our quartz crystal. Right now, our plane polarized light is vibrating in a north-south direction, and so we're actually aligned with refractive index epsilon of our quartz in this view. Let's rotate our quartz crystal now and see if we notice any pleochroism. And as we start to spin the quartz crystal, you can see, well, nothing's really happening here. So because our rock crystal is clear to begin with, there's no coloring agent to cause differential absorption of light as we're looking through our crystal. And so we don't actually see any pleochroism with the clear quartz. This will be a little different for our later varieties of quartz, which actually have coloring agents and so can differentially absorb light. So let's return our quartz slice so that we're viewing again down the c-crystallographic axis. And this time we're going to view our quartz slice with crossed polarizers. But first, let's bring in the optical indicatrix, and we can talk about theoretically what should happen when we bring in our upper polarizer. Because our plane polarized light can only ever interact with refractive index omega in this view through our quartz crystal, essentially when we bring in our upper polarizer, the quartz should remain extinct, and should remain so when rotating our quartz crystal with crossed polarizers. So let's bring in our upper polarizer now, and of course everything will go exactly to plan. Nothing could possibly go wrong, right? And that looks pretty wildly different from the theory I just described. So what's going on here? Really, there's two different things going on here with our quartz crystal. Let's just focus on the neon colors that we can see first. And these colors are a result of the optical activity of quartz. So in investigating this phenomena, we actually want to go back to the structure of quartz, which consists of helical chains of silica tetrahedra that parallel the c-crystallographic axis of our quartz crystal. And these helical chains of silica tetrahedra do something pretty interesting when our plane polarized light interacts with the structure of quartz. They cause our plane polarized light to rotate as it travels through the quartz crystal. And the rotation of our plane polarized light actually depends upon the frequency of the light. As such, there is dispersion as well between the different wavelengths of our white light. A much deeper dive into these phenomena can be found in this article, Quartz, a Bullseye on Optical Activity. But for our purposes today, we just need to acknowledge that quartz is not behaving like a normal uniaxial mineral would in this situation, and that's due to the quartz structure made up of those helical chains of silica tetrahedra traveling parallel to the c-crystallographic axis. Also, you should note that if viewing quartz in thin section, the thickness of the section is insufficient to show off this optical activity. So you're only really going to see this associated with quartz in thicker sections, and it's a great way to identify something as quartz. For this quartz slice in particular as well, I didn't quite get it perfectly looking down the c-crystallographic axis, and that's actually why we have the tie-dye color effect. If I had gotten it perfectly cut, you'd just see one solid color as we looked across the crystal. So I think that's sufficient for our dive into the optical activity of quartz, but now let's focus on another phenomena that's going on with our quartz slice here. So I want you to notice these triangles highlighted in the red oval. You can notice a couple other small ones around the edge of the crystal as well. And these are actually Brazil law twins in our quartz crystal. So our viewing setup of looking at our quartz slice with crossed polarizers is a great way to observe this twinning. And the reason we can see this twinning takes us back to the structure of quartz. So our quartz structure consists of those helical chains of silica tetrahedra spiraling parallel to the c-crystallographic axis. Those chains have two different ways in which they can spiral. One left-handed and the other right-handed. And this is why we have the two different space group symbols for our quartz, P3221 or P3121. So with the Brazil law twins, what you're seeing is an area within the crystal where the spiral of the helical chains of the silica tetrahedra is actually opposite that of the rest of the crystal. And if we wanted to, we could use some optical phenomena in order to figure out which way those helical chains of silica tetrahedra were spiraling. Let's leave that for some other time, however, and I'll refer you to this paper if you want to learn more on the subject. So let's get back to our quartz slice with its optical activity and its Brazil law twinning going on. And I think that's about as much complication as we want to deal with today. I think if I wanted to make a brand for quartz, it would probably have to be Quartz. It's super common and super complicated. Let's rotate our quartz crystal now with crossed polarizers and see if anything else interesting happens. Remember, if we were looking at a normal uniaxial material, when we were rotating it with crossed polarizers in this viewing direction, it would stay at extinction the entire time. However, with our quartz crystal, we're seeing a manifestation of quartz's optical activity, along with my failures as a lapidary for not cutting everything perfectly aligned with C. Now that we've explored our quartz slice looking down the c-crystallographic axis with crossed polarizers, let's do the same for the view through our crystal looking along the plane of the A-axes. And I promise, the quartz will not be nearly as complicated in this direction. So let's bring in our upper polarizer now, and you can see that in this orientation our quartz crystal is at extinction. And that's because at the moment our plane polarized light is aligned with refractive index omega of our quartz crystal. As we begin to rotate the quartz crystal, light starts to transmit through our upper polarizer. This is an interference color. Our interference color here reaches a maximum brightness at 45 degrees from our previous extinction position, and as we continue rotating the crystal, we eventually reach extinction again as we line up our plane polarized light with refractive index epsilon of our quartz. So when looking down the plane of the A-axes, we've had pretty normal uniaxial behavior from our quartz. It's really looking down the c-crystallographic axis where quartz shows some unique behaviors with its optical activity as well as twinning. With our quartz slice, we can also generate an optic axis interference figure. So let's return to a view of our quartz slice in plane polarized light, viewing down the c-crystallographic axis. And note I had to change my focal distance here in order to get everything to work properly for our optic axis interference figure. In order to generate an optic axis interference figure for our quartz, we're going to need to bring in our upper polarizer and have our view be with crossed polarizers. And then additionally, we bring in a converging lens. I'm using a hand lens here. Depending on the setup of your polariscope, the converging lens may also be underneath your upper polarizer. So we've generated an optic axis interference figure for our quartz. However, it doesn't look like the standard uniaxial optic axis interference figure. And if you want a refresher on uniaxial optic axis interference figures, you should check out Optical Mineralogy Improved Uniaxial Optic Axis Interference Figure video. But this quartz optic axis interference figure looks pretty similar to a uniaxial optic axis interference figure. However, the center of the figure appears to have been replaced by a purple circle. And this modified uniaxial optic axis interference figure is actually a result of the optical activity of our quartz that we talked about earlier. So this also makes the generation of this optic axis interference figure pretty diagnostic that the material you're looking at is quartz. Moving our converging lens over different areas of our quartz slice shows that there are some regions where the quartz uniaxial optic axis interference figure actually begins to distort. These are regions in our crystal where Brazil law twinning is going on, and if you actually had an appropriate Brazil law twin, you could generate what's known as Aries spiral. And that is a whole different can of worms for a different day. So our simple clear quartz slice actually has quite a few different interesting things going on that you can tell just using some basic techniques of optical mineralogy. And now that we know the phenomena going on with our clear rock crystal slice, let's actually take a look at some of our other varieties of quartz as well. So here we have our slice of smoky quartz. We're viewing this currently in plane polarized light vibrating in a north-south direction. We are looking down the c-crystallographic axis of our smoky quartz and taking a look at the optical indicatrix for our quartz. In this viewing direction, our plane polarized light can only interact with refractive index omega, and as such, as we rotate our quartz crystal, no pleochroism should occur. And no pleochroism to speak of in this direction. What you can notice in this viewing direction, however, is that our smoky quartz has some color zoning going on. The distribution of our coloring agent isn't uniform throughout the entire slice. Let's take a look at our smoky quartz now, looking down the plane of the A-axes. And so right now we've oriented our quartz slice so that our north-south vibrating plane polarized light is aligned with refractive index omega. And as we rotate our quartz slice, you should notice that it actually grows gradually darker in color. It's not a huge change, but there is a bit of pleochroism going on with our smoky quartz. And so refractive index epsilon is associated with a slightly darker color of our smoky quartz. Here's images of our two different pleochroic end member colors side by side, so you can hopefully spot the less than impressive difference. Let's return our smoky quartz crystal to a view where we're looking down the c-crystallographic axis, and let's check out what happens when we bring in our upper polarizer and view the sample with crossed polarizers. So just like with our rock crystal quartz slice, what we see here is a manifestation of the optical activity of quartz. In addition, along the edges of this quartz crystal, we can also see small Brazil law twins. Let's now take a look at how our smoky quartz crystal behaves when looking down the plane of the A-axes while viewing the sample with crossed polarizers. So here we are looking down the plane of the A-axes for our sample. Right now our plane polarized light is aligned with refractive index omega, and we'll bring in our upper polarizer and see what happens. So at the moment our sample is at extinction since our plane polarized light is aligned with refractive index omega. As we begin to rotate the sample, light will start to be transmitted as an interference color, and we eventually rotate the sample enough so that we've aligned our plane polarized light with refractive index epsilon, and our sample goes back to extinction. So our smoky quartz slice has behaved very similarly to our rock crystal slice that we looked at earlier, the main difference being that the smoky quartz slice can display a bit of pleochroism. Let's check out an optic axis interference figure for our smoky quartz slice. So we return to a view of our smoky quartz slice looking down the c-crystallographic axis. We bring in our upper polarizer so that we are at crossed polarizers. and then we bring on an additional converging lens in order to generate our optic axis interference figure. And the behavior here is unsurprisingly very similar to that which we see with our rock crystal quartz slice. I think those were all the fun experiments we wanted to do with our smoky quartz. So let's check out our amethyst slice, which unfortunately will be a bit more limited in the phenomena that it can show to us. So we are currently viewing the amethyst slice in plane polarized light vibrating in a north-south direction, and we are looking along the C-axis of our amethyst crystal. And one of the things I want you to notice with our amethyst slice is that it's a bit different than our smoky quartz slice. In this case, the amethyst has some pretty strong zoning that you can see in the distribution of the purple color within the slice. And the other thing unfortunately going on here is the amethyst slice is all sorts of included, and it has iron staining along the edges of the amethyst slice. So these problems and complications prevent it from being as useful as our other cleaner quartz slices that we've looked at earlier. But it's got one thing going on that's pretty awesome and makes it unique. And so let's bring in our upper polarizer and take a look at our amethyst slice with crossed polarizers. So our other quartz slices showed off their optical activity with this view, but with our amethyst, what's actually going on here is quite complicated. And so what we're seeing is the effects of polysynthetic Brazil law twinning. So our other quartz crystals also had some Brazil law twins. However, with our amethyst, these twins are polysynthetically stacked in such a way that we end up with this interesting pattern. And if you recall the pattern in the color zoning that we saw in our amethyst in plane polarized light, it looks very similar to the pattern we're seeing with our Brazil law twins with crossed polarizers. If you want a deeper dive into what's going on here, I suggest checking out this paper. So this behavior of the polysynthetic Brazil law twins is really what I wanted to show off with our amethyst slice, and so I think we'll just stop there. Someday I may try and purchase some pricier, cleaner amethyst in order to use our amethyst slice for some other things, but we'll save that for another time. Instead, let's go check out our last remaining quartz slice, taking a look at citrine. And I think you actually already have all the knowledge you'll need to interpret what's going on here with our quartz slice, given what we looked at with our rock crystal slice and our smoky quartz slice. So I'm actually just going to be quiet now and let this next segment of video run and see if you can understand everything that's going on without my yammering. One last note, this citrine slice has some pretty cool zoning going on. However, not all of the citrine slices will have this. So I hope that segment of video on the citrine slice made sense to everybody. And so now that we've looked at all the different types of quartz slices that we have, let's take a look at the big picture about quartz again. So our quartz is defined by its chemistry and structure. This chemistry and structure in turn leads to the macroscopic crystallography we can see and that we examined in a macroscopic quartz crystal. The chemistry and structure also causes our optical properties, which we examined over a variety of quartz slices. In particular, quartz has some very interesting and unique optical properties caused by those helical chains of silica tetrahedra spiraling parallel to the c-crystallographic axis. This structure is ultimately responsible for the optical activity of quartz, the Brazil law twins that we can see, and the unique uniaxial optic axis interference figure for quartz. Remember, quartz. Super common, super complicated. So here's a chart detailing our different quartz slices and what they're good for. I hope you'll consider purchasing one of these from Snellius Minerals. You can find the eBay store located at the following. These quartz slices are all cut from natural quartz crystals, and so there will be variations between these. If you have any questions, comments, or concerns, feel free to reach out to us via email at snelliusminerals@gmail.com. And here's a list of references I consulted in the construction of this video. Thanks again for watching this video. I hope you learned something, and have a great day.